What's going on, everybody, and welcome to part 3 of the BCI tutorials. To begin, we have now a GitHub. So lots of people were asking for code and stuff like that. I put that up, as well as training data, as well as models and their validation and all that. So a little bit more on that towards the end, but just know it's up there now, so anybody can follow along. If you have a headset, you can use the code that I'm using to create training data, test that training data, analyze and validate that training data, all that. You also can grab from our best models and see how they work for you. One question I do have is this anecdotal, so to speak? Are the models that I'm training really only going to work for me? I have no idea, no clue. So anyway, love to know the answer. And if you don't have a headset, you can still do things like train models. Also, at some point, it could be beneficial. For example, anybody can download the OpenBCI GUI, and then you also can actually play back from files. So it's possible I could even create some playback files and put those up and explain what the goal, what I'm thinking in the playback file, and then you could run that playback file, and then you can basically synthesize or simulate having the headset without needing to spend $1,000 or $2,000 or something like that. Also, you can generate from synthetic data. I don't really think we have a use for that at the moment, but anyway, lots of stuff that we can go from here and allow people to follow along and actually try their own stuff. And also, you can try to train your own models and beat our current results. So, okay, cool. So from the last video till now, I believe kind of where I left off was I definitely had a model that was better than random. So, and then I think it was maybe a little unclear to some people. There's 3 possible actions in the validation data: left, right, or none. So random would be 33%. So if you're getting on average about 40+% accuracy, that is better than random. You have an edge, and given enough frames, you will go the direction you intended to go. Okay, so now things have improved considerably, and I'll be showing some of that and some of the issues that we've run into along the way, as well as some of the things that we have to think about moving forward into the future. So with that, let me just dive on in. So let's see, I will just open up kind of, so mostly these versions are kind of just me running through the code and like trying different things. So the version 1 through 3, I think, yeah, this was like raw signals. I tried networking on V1, but it didn't work because of the 16 and 125 channel thing I talked about before. But eventually I figured that out, started V4, and then V5 is all about fixing overfitment issues, which we will talk about right now. So one of the things that I found was when I would actually run validation, it would be very inconsistent. So first of all, when I would just train a model, I would get the in-sample data to 85 to 95% accuracy, and then even the out-of-sample data would also be 75 to 85% accurate. I was getting huge accuracy while training a model. So to exemplify that and to explain what was going on, because this is not BCI only. So as I will make clear, this is a lesson I've learned at least 2 times in the past, and it just keeps smacking me in the face. So hopefully I can share with you guys, and maybe you guys will remember better than me about this issue. So so let's see, where is a model train? So proper validation. I'm not even sure what the difference of these two are. Let me pull this up, because this one might be I'm not even sure. Like one of them, this might even be prior to the validation directory. That's my guess. Training data. Nah, this one still has it. Unfortunately, I don't even have the original script because I got rid of it. But basically what I was originally doing was I was going into the data dir, loading in left, none, and right data, and then I'd create the samples. And just to be clear, what each of these directories contains is a NumPy file where the name is just the timestamp it was created. So here is a bunch of NumPy arrays that are 250 samples long, basically there are 250 samples of individual 16-channel FFT graphs, or fast Fourier transform graphs. So because I pull from pi LSL at a static rate of 25 iterations per second, each of these files is 10 seconds of me thinking this direction. So the first thing I did was load up all this data, store it into like a list of fast Fourier transform and the actual target, which was converted to a one-hot vector. So left 1, 0, 0, right 0, 0, 1, none 0, 1, 0. Okay. So I made a big list of those, basically. And then the first thing I did to create out-of-sample data was separate it entirely by saying, okay, what I want to do is first create that big list, shuffle that list, and then take the last 10% of that list. That's your validation data. And then obviously don't train on that data. Well, that's fine for like typical classification tasks where you've got these truly separate samples. The problem is often for sequential data, so the first place I learned this was on finance data. I'm doing 25 iterations per second. So it's 25 iterations of 16-channel fast Fourier transform data. So from that 25th of a second to the next 25th of a second, that fast Fourier transform is very similar. It will change probably not much. And I know it doesn't change much because we overfit. So the first thing that I decided to do to overcome this was actually, okay, so instead of taking each taking random samples theoretically from each file, because this basically means the out-of-sample data, it's almost certain that the random samples in the out-of-sample data almost identically will match samples in the in-sample. So this is going to just for sure cause overfitment. And it did really well. So then my thought was, okay, what I'll do then is, because each of these are a separate 10-second interval, and it's not even a sequential, so it runs for 10 seconds, it breaks, I have to rerun the program, things change, my posture changes, all kinds of things are changing between each file. So I thought, okay, so then to make the first true validation, the one that I put up on GitHub first, I took just random files. I would just click this one, then this one, then this one, then this one, and I just moved them to a validation directory. And the result there, now I can actually start showing you things because I actually retained the code. The result there is the following. So let's say, let me go ahead and we'll just run this. And the first thing I'll do is, so analysis.py, basically I kind of measured accuracy in two ways. So one of those ways was to do validate. So let me just pull up both of these. So one way is to actually validate the model. And the way I was doing that is, okay, specify the model name. And then what I want to do is actually go and access the validation directory and then run through, make the predictions, return that information, possibly make the confusion matrix, which is what you're going to see in a moment. So that was one way. So one way of validating the model was to do exactly what I did as I trained the model, use the validation data, which I just explained was me pulling those 10-second files. So if we do that, we'll just do that. Well, let's make sure it's the same model. That's probably important, huh? So which model do we use here? 63, 23. Let's just make sure. Let's get on 252. Okay, yeah, they are the same model. Cool. So so first, let's do the validate.py. So we'll say Python 3711. Cool. This might take a moment. I can't. Well, I think we batched through it, so it should go pretty quick. Maybe. Yep, there it is. Cool. So here we have the confusion matrix for that model, which is stellar. I mean, it's basically 60% accuracy at the worst, right? So this is the action thought, and then this is the predicted action. So in this case, I'm thinking left, and 58% of the time, it correctly predicts left. And then 9% of the time, it thinks that's maybe a non-action. And then the other 33% of the time, it thinks right. So one thing that I did know for sure is the model is actually pretty good at figuring out if you're not thinking left or right. But then when you are thinking left or right, it's going to miscategorize most often the other direction, right? So then, when I'm thinking nothing, it's a pretty good balance between incorrectly predicting right or left, but then it was 70% accurate of knowing, don't go that direction, or don't go none. Or go none. Anyway, whatever. And then right, it's kind of same story. 61% correct, 27% totally incorrect, right? So one thing you have to think about is if you are thinking, hey, don't move, it's very bad if you do move. And then if you are thinking right, it is worse to think left. Like if you want to go right, it is way worse to go left than it is to just do nothing, right? So the difference, that's why the confusion matrix is useful, because we can actually see, like, okay, there are certain classifications that are worse than others. So anyway, regardless, that looks really good. But then in practice, it didn't look as good. So the other way I validated my models was when I actually go to train them. I'll have to pull up another script. With clipping. Okay, clipping I'll explain later. When I actually go to train them, and these are just previous models that I used, and I like, if a model seemed to go pretty good when I actually was using them, I just kind of saved them to comments. What the heck was that? Oh, right. So this is the script that I showed in the previous video, where I just say, hey, please store this data in the left directory. So the program itself, or the script, doesn't do anything else with this action other than, hey, I'm just notifying the program, hey, save this under lefts. Otherwise, it has no idea what left even means. So yeah. So coming down here, at the end of the session, like, this is the script that I run while I wear the headset, while I'm basically kind of testing a model out and creating more data at the same time. So I am running this model that's taking the fast Fourier transform, shooting that through the actual model itself. If I could find it, yeah, out model.predict. We print that out just to see it, and then we go based on the argmax and actually start saving information and moving that box wherever we predict it, and that's that OpenCV. It just moves the box left or right. So cool. So okay, so that's all that does. But one of the other things it does is it opens up this accuracies.csv, and it saves the time, it saves the intended action, it saves the percentage accuracy of that action just specifically, it saves the specific model name, and then it saves all these. It saves the actual percentages for each of the actions. And that's how, so I can make also a confusion matrix on this data, which is the most realistic forward test you could possibly do, right? It's truly live. It's not validation data. So when I do that, I get a little different answer, because that's what 9 does. So what have I done with part 9? Yes. So part 9, analysis, reads from that accuracies file, not the validation data. So this is the truest out of sample we could possibly have. And when we run that, Python 3.7, and then we go 9. And again, this is off of taking the entire files, not just random samplings from the entire data set. On that exact same model, that's the confusion matrix we get, which is quite a bit different. Wait, I can't quite fit it all on screen. Anyway, it's quite a bit different than the other one, right? So it is still impressive. It's still accurate. It's right more than it is wrong, but it's different. And this kind of makes me wonder, like, well, what the heck is going on here? Oh, also, these are in... So the confusion matrix, unfortunately, has different values here. This one goes left, right, none. This one goes left, none, right. But sorry. But you get the idea. It's still clearly the middle numbers you can see are very, very different. The reason I noticed that, I was like, that's weird. This model didn't get none is wrong. And then I was like, oh, no, it's just different ordered. Anyway, we have a problem, because what this is supposed to be validation out of sample data. I believe I did a good job at separating out the validation after I was like, oh yeah, that's right, sequential data, blah 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 blah. You know, the data that is 1/25th of a second separated from the in-sample data. Of course that fits. That's going to overfit, right? In this case, I was a little more surprised to find this much of a difference. Okay, I guess we're still. And so it's like data from the same sitting is a problem, which is very interesting. And the data is taken over the course of multiple days, multiple sittings. I would take off and put back on the headset. I was sitting, standing, eyes open, eyes closed. There's a lot of variation to the data, so it is kind of odd. But okay. So my next thought was like, okay, well, how can I just mimic this live data as best as possible? The only way I could think is to just separate out an entire different day's worth of data. That's the best I got. So then that's exactly what I did, and that leads us into v5. So we leave v4 and we come into version 5, overfitment fix. So now what I will do is I'll do the exact same thing. We're going to run, we'll run the same kind of test. So analysis again is running off of live recent data, and then what have I done? And then 11, validate model, is running off of, so one thing I should probably do before I cry is get rid of the older ones. So these are both from v5, yes. Okay, so this all, again, let's confirm that we're using the same model for a comparison, 6323, 252 loss, blah, 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 yes. And they're both from GitHub model, yeah, okay. Okay, so again, same model, but different data. Let us grab, not from this is in v4, I'll pull over v5. So now I will just run python 379 analysis.py. Okay, and just for the record, this is actually, I'm trying to think. Actually, no, this is this. I think this is the exact same model that we just pulled, because these are both the GitHub model that is just a clipping model, if I recall right. 6323. I'm pretty sure that's the one that we were just looking at. I'm going to confirm just to be 100%. Not that it really matters. Mostly we're just trying to show in sample versus out of sample, but I believe those are the same models. Yeah. So sorry, I have to confirm because I've used so many models, and like every time I add more data, I train a new model. And I just continue that process, and it's been really cool to see how over time it's actually gotten better. Like the first models I trained were terrible. It was very frustrating to like be trying to think left and then the box goes right. That's just it's just very, very frustrating, especially when people are saying this is not possible. And then, but I'm like, I'm pretty sure it is, especially like left, right. That should be totally doable via this data, or so is my belief. And so people are like, no way it's going to work. And I'm like, I think it will. But then to find out if it works, I'm sitting here with a silly thing on my head, staring at a screen for hours, trying to move a box with my thoughts. You start to question yourself. So I'm glad that I'm seeing some results. We'll talk about why they could still be problematic moving forward. But yakety yak, I already forgot which one we ran here, so I'm just going to rerun it. Okay, so we're running analysis on v5. Now let me run Python 3.7.11 validate model. So this one will actually go through the validation set with the model making predictions, as opposed to this one just simply reads the results from my live retraining. For some reason this is oh god. I was like, oh my gosh, it's killing me because this is the same one. But of course, I'm running it in v4. Whew, what a panic. Why am I? It says v5. What's going on here? Oh, it was the, this is what fooled me. It's the, oh goodness. More coffee, please. Okay, now back to being sane. Python 3.7.11 validate model. That was funny. Cracked myself up. Okay, so hopefully it'll be close to this, or nearly identical, but we'll see. Okay, so this is using the validation data, although this is still not in the right order. I kind of want to fix that real quick just so it is identical, but I don't really want to make that fix live. But as you can see, there are some slight differences, so left is a little different. If we think left, the mistake to go right is slightly different, but basically the same, and then none is actually identical. None and none is off by a little bit, but pretty much these are the same. Right, 15, 33, 52. Oh, this one's actually identical. Anyway, this is what we want to see. So I'm very happy that, okay, finally I am confident in our out of sample, and the way that we have to do that clearly is to just take a completely separate day. Unfortunately, I don't really like that either, because to me, I thought it would be a better out of sample to take many days. And maybe that's what I'll have to do, is as the data set grows, I'll just take, right now I'm only taking 1 day, because 1 day is like, that's a lot of my data, right? So I don't really want to dedicate whole days to validation data, but that's clearly what I'm going to have to do to get a really good general idea of how accurate are we actually getting. So moving forward, I'm just going to have to keep creating more data, and then dedicate some days of data specifically to validation data. That way we get a good spread over time, because just 1 day is, in my opinion, too anecdotal. I really wanted to grab the random samplings, but you just can't do that apparently. So anyway, that was an interesting finding, but also a thing that I've experienced before, especially with finance data, and just deep learning in general. You often will find yourself cheating even when you don't intend to. So there you go. But this is cool. The fact that I have a model that is accurately predicting all of these across the board, more than random, in a true live setting, finally, that I figured out how to do that. Apparently I'm an idiot. That's so cool. Like, that is really cool. Like I said, it was very frustrating, and it still is. It still sometimes goes the wrong way, but it's pretty cool to sit there and think left, think right, and move the box. And then it's hard for me to create the data this way. I'm still trying to decide how I want to make the environment, but it would be also cool to like think left and then change direction right, and then left, none, hold still. That's kind of the next succession here, is somehow create an environment that does that. And I can't decide if I want to put like a little dot on each side, or maybe say like left, right, up top. Just trying not to have some sort of artifact that shows up in the data. And again, I don't know what will. So taking that to the next step is, like, let's say you have a dot on the left or the right of your screen. Well, that could influence just eye movement in general, which could then inform the machine. So, and then the other thing that is possibly problematic here is EMG data. And so a lot of times, so in the previous video, a lot of people were suggesting, why don't you actually press keys? Well, if you actually press keys, these muscles will be activating, and that shows up. And so you don't want that. So that's also a way that the model could be cheating right now, is as I think left, think right, I might be getting these like little muscle twitches, and that might be showing up too. Also, if I'm moving my eyes left or right, that shows up. The eye movement shows up really good. Or if I flex my eyebrows or something, or I clench my teeth or do any of that, that shows up, right? So just muscle flexing shows up. You're getting more than just EEG. Now, apparently, I know nothing other than the claim that we can do it. Apparently, within the GUI, maybe, I can't remember, there is a way to filter out or at least detect EMG. So one of the things I'm going to be looking into moving forward is figuring that out. How do we go about doing that? But obviously that's something I have to figure out. So, and then I also have to kind of decide, do I care? Like, as long as I'm not actually moving that body part, right? I'm not sure I actually care all that much. Like if I think left and my eye has some sort of crazy subtle twitch that I have no idea about, I mean, picking that up is still kind of cool. So I just, you know, I don't know. But I think the purest thing would be, indeed, do it just with brainwaves. That way, like the idea is that people could use this to control a motorized scooter or something like that. So if they don't have arms or legs or something to twitch, it's important that it still would work, right? Like it would still be that's necessary. So yeah, so I'm gonna try to look into that stuff moving forward. And then now that I'm actually getting somewhere, like this is pretty basic. I'm gonna explain this along with the GitHub soon in this video. But I'm getting somewhere now to the point where I actually am controlling that square. So now I can start applying this to things. Besides just staring at a block on my screen. And I can just kind of change the environment in a way I can still continue to collect data. So I'm not sure where I want to apply it yet, but we'll see. I've got lots of ideas. So stay tuned for that. Hopefully by part 4 I'll have something way more exciting than the silly OpenCV block environment. So cool. So now let's talk about the GitHub environment and what we've got going on there. So close. So yeah, so basically everything is here. The training script, basically simple enough. It just trains a model. And again, I think I showed it in the last tutorial, but this is just a basic model. It's just a 64 by 3. Woo. And everybody in the back see it. But even just this model is pretty accurate. This will still get you to, you know, mid 40s for all of the actions. But one of the things that actually isn't even in, I should add it to this because I actually have it now, I think, in the training, but I don't see it here. So for me, I just did the 64 by 3 one-dimensional ConvNet, and that does pretty well. Also, people were asking about ConvNet versus RecurrentNet, and some people just like, I don't know, they don't believe me. I don't know. I feel like I've been here long enough that if I say something, I'm probably not BSing. But also, you could just go to Google, right? So if you Google 1D ConvNet with attention, you should be able to find some research papers on this. But then also, if you look at typically sequential data tasks and just see what are people actually doing nowadays, you will see that people are shifting from recurrent nets to 1D ConvNets, usually with attention. And they're doing this for 2 reasons. One, it trains much faster. And because it trains much faster, you can much more quickly iterate your model. So you can actually train a model, you can get it done faster. So you can figure out where to go much quicker. It can run in practice much quicker, but also people are doing better. So the latest thing that I used this with was the text to speech. That was a deep convolutional text to speech model. It was a 1D ConvNet with attention. But that's just one of the many things that people are doing with ConvNets and attention to just vastly outperform in like every freaking way possible recurrent nets, which is pretty cool. Especially because there's so much more research and there's so much more attention being given to convolutional neural networks and getting those to go fast. So very cool. Anyway, that's what I'm doing. There is something to be said though, like I am not passing sequences to this ConvNet. This is making predictions 25 times a second on a single frame, which is the 16 channel fast Fourier transform. That's it. And just as a reminder, that looks like this is a single channel here, which I'm not making predictions on. This is basically what the model sees, only in numerical form. It's not a beautiful, pretty graph like this. But yeah, so this is what it's making predictions on. So it definitely stands to reason that possibly using a sequence of data would be a good idea. Totally possible. I have not tried it. I want to say Daniel said he tried it and he didn't find much benefit there. But one thing Daniel did do was clip the data. So I want to say he clipped it at 3. And then also possibly, or no, I think the model we're using clips at 10 or something like that. Let's go to maybe models. and then the README. So this is the one that I used to get a pretty decent accuracy. And then this one is currently the best performer, which, yeah, clips at 10. So we're just running a clip over that NumPy array. Really basic. So that's our way of kind of scaling the data. So I'm really not doing anything else. The only pre-processing is the fast Fourier transform, which is definitely pre-processing. And then now clipping the data, thanks to Daniel's idea to do that. But even before clipping it, it was pretty accurate. So the information is definitely there. And again, this is just on one frame. So I think doing a sequence of data would help, and this needs to be updated with the graphs that you see here. So this was very recent that I was like still racking my brain on like, well, why is in practice this not as good as the validation data? Like in practice, you should be identical to the validation data. So anyway, I will update this, but because this is not true, this is the best model, but this was on that validation data, which had a little bit of in-sample leakage, I guess. I don't know. Anyway, cool. So if anybody wants to take part, you can. You don't need the headset to try to make these models. If you think you've got a better idea, you have to kind of use the fast Fourier transform because that's what the data is. But I have hosted all of the data, and I've hosted now the V2 of the data, which you can find by scrolling down, maybe. And then back, so you go down and then you go back up to here, this link here. It's just on hkinsley.com. I just don't know really where I want to stuff the data right now, so it's just there for now. And that's about it. I will continue to update that, especially if I find some even better way to do out of sample, but also as I build more data and then I get more out of sample days, so to speak. I'll continue to update that. Right now, I think it's about 750 megabytes of data per action, which is quite a bit, but it'd be nice to do more. And we still have the problem of in-sample overfitment. So when you go to train a model, your in-sample accuracy is going to be like 85% to 95%, but your out-of-sample is going to be like 50 at best. So the solution there is unfortunate. And that's happening because from sequence to from fast Fourier transform to fast Fourier transform, they're very similar. So the model learns very quickly because the data is so similar to previous data that it's seen, even intra epoch. So the solution there is to maybe before you pass the data to the neural network, don't use every sample. Use every 5 samples or every 10 samples, right? But of course, this mutilates the training data that we have to be 1/5 of the size or 1/10 of the size. But once I have enough data, maybe that won't matter. So I think that's the solution to fixing the out of sample. The other one could be possibly training on sequences, but again, from frame to frame, you're going to still have the same issue. So surprise, the solution is much more data so that we can throw away a bunch of samples. Okay. I think that answers probably everything that gets us up to where we are, but also, yay, GitHub. Let me see here. Is this one? Did I fix this one? No, this one's still bad. I need to update both of these now that I didn't want to update the charts until I had uploaded the new data set because then people would create them. So if you want to try this, you can train a model using the train.py. Again, it's just a really simple example of a model. You can do whatever you want, right? And then once you've trained your model, go ahead and run the analysis.py, and that will create the confusion matrix. And the one that we're looking at right now is just percentage accuracy, but I've got a couple other ones that you can graph if you so choose. And if you got something that's better, cool, share it with us. I'll check it out, and I'll definitely attribute you if you come up with something really good. So there's that. And then finally, if you do, I know some of you might get the wild idea to train a model on the validation data. So if that's you, I will be having 2 validation sets, and I will confirm models on both of those sets. So don't do that. Please don't waste my time. So anyway, I think that's everything. Questions, comments, concerns, suggestions, whatever, feel free to leave them below. If you still think it's impossible to do it, let me know. It's still possible. Maybe it's all EMG. I mean, maybe that's what's happening. Maybe it's only making predictions on EMG. Who knows? So We'll see. Hopefully I can figure out how to filter that out. I'm told like it's possible. Hopefully I don't have to make all new data by doing that, but that's also possible. But I'd also possibly like to save the raw data. I haven't been saving all of the raw data. And I think probably my next step will be save all the raw data. Because then if we save all the raw data, we could also create synthetic files that could then be passed through and all that. So, and then again, people could do things without the headset, but then also people who think fast Fourier transform is stupid could apply whatever the heck they wanted. So anyway, I will do my best to continue to provide everyone with as much data and stuff as possible so they can take part without necessarily needing to buy the headset, but the headset is pretty cool. That's it for now. And finally, shouts out to recent channel members, brand new Farron, Stanley, Harsha, Vardon Reddy, Nagasaraj, Victor Douay, and Bill Fujimoto. Thank you guys very much for your support. Without you guys, we would not be moving things with our minds. Okay, that's all. Till next time.